Next, we see confidentiality and integrity. Okay. First, we saw authentication so far. Now we are seeing the confidentiality and the integrity part of it. Okay. So, WEP was designed to provide message confidentiality, integrity, and access control. But then it failed on all the three counts. We saw how it failed on authentication. Now we'll see how it fails on encryption and integrity checking. Okay. Now WEP, it uses the stream cipher RC4. Okay. Now what is this stream cipher? That makes use of a pseudo-random key stream we have seen. Okay. Now this key stream is a function of the static key that is shared between the AP and the station. Okay. So in order to create the key stream, we have already seen it makes use of the 40-bit shared key and the 24-bit initialization vector. This initialization vector, we said, is pre-configured by the manufacturer into the mobile station. So 40 plus 24, it becomes 64-bit key. Okay. Now, this 64-bit key, of course, the size is very small, one thing. Secondly, this shared secret is common. Okay, it is, we said the AP shares the same secret with all the mobile stations. So all the mobile stations have the same 40-bit secret key. So the only variant is this 24-bit initialization vector. And if that is going to be the same for all the messages that the station is going to send to the AP, then it is very easy for an attacker to get hold of this 24-bit IV. So in order to overcome this, one suggestion was to use a random per message initialization vector. Instead of using the same 24-bit IV, you use a randomly generated initialization vector for every frame that you send from the station to the access point or AP. Okay, now what does the station do? Okay, it has got the key stream. Okay, key stream is a function of the shared key and the initialization vector. Okay, now it has got the plain text that is to be sent from the station to the AP. Okay, so it will XOR the plain text with the key stream. This together forms the ciphertext. Okay, so the station will XOR the plain text and the key stream that forms the ciphertext. So WEP frame, when you take, it consists of the plain text. Okay, now along with this text, it will add a 32-bit CRC, okay, for encryption. Okay, so it uses a 32-bit CRC. So the plain text is concatenated with the CRC, and we said it is going to send the IV in the clear. Okay, so it adds the IV, it adds a MAC header, and together is what is called as the WEP frame. That is the frame that is sent from the station to the AP. Okay, so that the frame that is sent from the station to the AP consists of a MAC header, which is added to the concatenation of the IV 24 bits, the plain text, and a 32-bit encrypted CRC. Now, at the receiver, it receives this. Okay. Yeah, it receives this ciphertext. From the ciphertext, how does it get the plain text? Okay. To get the plain text, it will XOR the ciphertext with the key stream. Okay, again, the key stream is a function of the shared key and the IV. Okay, IV, the AP has got from the WEP frame, that is, you have the IP that is sent in the clear and then the plain text. Okay, so from here it gets the IV, the shared key, it already knows, so it creates the key stream and then XORs it with the ciphertext. Okay, so you have got the ciphertext, you are XORing with this. Okay, now what is C, we have already, how does the station create the ciphertext? It is plain text XORed with the key stream. So plain text XORed with key stream is the ciphertext. Now the receiver is XORing it with the key stream again. Okay. Now when you XOR these two, it is all zeros. Okay. So what you land up with is the plain text. Okay. So that is how the receiver gets the plain text. What is the problem in this? The main problem here is the key stream. Okay. We said that this is a 40-bit value. Okay. Out of these, sorry, it is a 64-bit value. Out of these 64 bits, this 40 bits is common to all the frames. Only the IV, that is 24 bits, is varying. Okay. Now 24 bits is varying means you can have maximum of 2 to the power of 24 different key strings. Okay. So with 24 bits, you can have a maximum of 2 to the power of 24 different key strings. Okay. So 2 to the power of 24 is a very small number which any attacker can get hold of. Okay. That is the main problem that was being faced with WEP. Yeah. Now suppose an attacker finds two frames which were encrypted using the same IV. Okay. Then what is it that he can do? Okay. The ciphertexts are different. Okay. Only the IV is the same. Okay. Using the same IV, he has got hold of two ciphertexts. Say they are C and C dash. And suppose the plain texts are P and P dash. That is, from P, he has got the ciphertext C. From P dash, he has got the ciphertext C dash. Okay. So the ciphertext is nothing but the plain text XORed with the key string. Now, the attacker has got hold of C and C dash. Okay. Suppose he takes XOR of C and C dash. Okay. XOR of C and C dash means XOR of P XORed with key stream, XORed with P dash, XORed with key stream. Okay. That is nothing but P XORed with P dash. Okay. Or the P XORed with P dash is the same as C XORed with C dash. That is, your P dash is nothing but P XORed with C XORed with C dash. Okay. So, knowing C, C dash and P, we can obtain P dash. P dash is P XORed with C XORed with C dash. So in this way, an attacker, if he is able to get hold of C, C dash and P, he is able to get the P dash. That is what is known as the known plain text attack. Okay. So this is the one problem with WEP. Okay. The other problem is message modification. The attacker can easily modify a message which the receiver will not be able to find out. Okay. Suppose you have a message and you are breaking the message into three parts, M1, F and M2. Okay. The same binary string you are dividing into three parts. Only thing is, what the attacker wants to do is this part F, he wants to replace it by another string F dash. Okay. So the message that the receiver will be receiving would be M1, F dash, M2. Okay. Will the receiver know that this is not a message that was sent by the sender? Okay. Using your Mac, will he be able to find out or will he not be able to find out? Is the question now. So the attacker wants to substitute F by F dash. Okay. Now suppose this is the message. What is it that gets sent? The sender will create the CRC of this message. This is your plain text now. Okay, so he creates the CRC of the plain text, concatenates the plain text with the CRC, XORs the entire thing with key stream, and the result of this is what the sender is going to send to the receiver. Okay, so this is the text that is getting sent. Yeah. So now, what does the attacker do? Okay, he wants to replace F by F dash. Okay, so for this process, so that the receiver does not know that somebody has manipulated this text, the attacker does the following. Okay, first he creates 0 to the power of mod M1 concatenated with F XORed with F dash concatenated with 0 to the power of mod M2. Okay, what is 0 to the power of mod M1? Mod M1 is the number of bits that were there in M1. Okay, so you put that many zeros, concatenate with F XOR F dash. Again, you concatenate with M2 number of zeros. Okay, next he takes the CRC of this value. Okay, then he concatenates this, whatever he has created in step 1, with what he has, the CRC value that he has calculated in step 2. Okay, that is our step 3. Now what he does, he takes the message, whatever he has received, whatever the sender has sent. Okay, we have seen that the sender is sending this message. Okay, that is the plain text concatenated with CRC of the plain text XOR with the key string. Okay, so plain text concatenated with CRC, the entire thing XOR with the key string. To that, he XORs whatever he has calculated in step 3 here. Okay, now when he does this, what is it that he will get? You see, M1, you are XORing with zeros, M1 number of zeros. What is it you will get? M1, any bit XORed with 0, you will land up with the same bit. Okay, so you will get back the message M1 itself. Okay, next you have F1, F concatenated with F XORed with F dash. Okay, so you will get, F XORed with F XORed with F dash. Okay, next you have M2 XORed with 0 to the power of mod M2 or M2 number of zeros. Okay, now that is again concatenated with CRC, this remains the same. Okay, and CRC of this, CRC of this and this CRC, that remains the same. And then you have the key string. Okay, now this is nothing but M1. This will give you F dash and this will give you M2. So you end up with M1, F dash, M2 concatenated with CRC of M1, F dash, M2, because again these are all zeros. Okay, and XORed with key string. Okay, so the receiver is going to get this message. If the attacker is going to send this message instead of this first message, the receiver, once he gets this message, what is he going to do? He is going to XOR with the key string. Once he XORs with the key string, he will get back this message. What will he do to check for the integrity of the message? He will take this, he will calculate the CRC and check whether that is the same as this or not. It is obviously going to be the same because the message itself is M1 F dash M2. Okay, and so there will not be any change. The receiver will not know that an attacker has taken the original message and has replaced it by this message. Okay, so the receiver is not able to find out that the message has been modified. How? By this clever combination of computations that the attacker has done and included into the message. So this is the problem with the WEP protocol. Okay, so to overcome this, they came up with wireless protected access protocol. Okay, what was the main problem in WEP? It is because they were using RC4. Okay, now RC4, now the whole world, they have established all the hardware and they are using this. Okay, but now they want to change. If they change the hardware, then again it's going to be very costly affair. So the IEEE, they didn't want to replace this. They didn't want to replace the hardware. They wanted to maintain the same hardware. So they made many changes in the software. That is what we call as the firmware. In firmware, they made the changes. That is, the software changes were made. And so what the overall design, what came up is what is called as WPA, the Wireless Protected Access Protocol. The official name for that is Temporal Key Integrity Protocol. Okay. Thereafter, they found that the problem is with RC4 only. After a period of time, they changed from RC4 to AES protocol. You know that AES is a much secure protocol. Okay, so this came to be known as the WPA2 protocol, or it is also known as the counter mode with CBC MAC protocol, or CCMP, or it is also called as the counter mode cipher blockchaining message authentication code protocol, or the CCMP protocol. That is the official name for WPA2. Okay, with AES protocol in place, all the problems, whatever was faced with respect to message confidentiality and integrity, were overcome. So in 802.11 protocol, the protocol that is being used is, the protocol that is being implemented is WPA2. Okay,